Domain of composite functions. Now that we've considered how to construct composite functions by plugging one function into another, we need to consider what consequences that has for the domain of the subsequent function. When considering the domain, there are two steps. First, we need to find the domain of the inside or input function. If there are any restrictions on the domain, we write them down. Second, we construct the composite function. Then we find the domain of this new function. If there are any restrictions on this domain, we add them to the restrictions from step 1. If there's any overlap, we always use the more restrictive domain. Once we have the domain of our new composite function, we can use that to generate the range as well. Continuing on with our example from earlier, let's consider the functions f of x equals x squared, g of x equals e to the x, and h of x equals the square root of x minus 2. We want to find the domain of each of the following compositions. The first one is f of g of x. So our first step is to write down what the inside function is. In this case, it's g of x, which gives us the function e to the x. So we think about what the domain of this inside function would be. E to the x has a domain of all real numbers. We can plug in anything we want into e to the x without any problems. So we'll say that x has to be between negative infinity and infinity. Again, we don't use the equal sign with the infinities. So our domain is everything. So now let's consider the new function, which is our composite function, f of g of x. So we take our g of x and we plug it into f of x, and we get e to the x all squared, which we said before was the same thing as e to the 2x. Now when we think about the domain of this new function, it's going to be the same as the domain of e to the x, because if we multiply anything by 2, that's not going to change the fact that we can plug in anything we want. So here, the domain of the new function is also all numbers between negative infinity and infinity. So now we look at the domain of the inside function and the new function to see if one is more restrictive than the other. It's not, and therefore the domain of the composite function will also be all numbers between negative infinity and infinity. We're going to do the same process for the rest of these. So let's move on to g of f of x. First, we start by writing down the inside function, which is f of x. That function is x squared. The domain of x squared is going to be all numbers. We can plug in whatever we want here. And then our new function from our composition is e to the x squared. And again, we can plug whatever we want into e to the x squared. So the domain of the composition is all numbers. And so therefore, since it's the same domain and one is not more restrictive than the other, the domain of the composite function is all real numbers. When we get to h of f of x, things start to change a little bit here. So f of x, again, the inside function, is x squared. And so the domain of that is all real numbers. However, our composite function now, we have to plug x squared into the square root of x minus 2. So we get the square root of x squared minus 2. Thinking about square roots, when we think about domain, we have to be really careful because we don't want whatever is underneath the square root to be negative. So it's really important that x squared minus 2 is always greater than or equal to 0. Well, if x squared minus 2 is greater than or equal to 0, we need x squared to be greater than 2. So here, we can write x squared has to be greater than or equal to 2. And we can use that to set up our domain. So if x squared has to be greater than or equal to 2, that tells us that x either has to be greater than the square root of 2, or x has to be less than or equal to negative square root of 2. Anything in between negative square root of 2 and positive square root of 2 is going to result in a negative number underneath the square root, and that won't satisfy what we need. So our domain here is more restrictive on the composite function than the inside function. So that's the domain that we use for the composition. So x is going to have to be greater than or equal to the square root of 2, or x could be less than or equal to negative square root of 2. If you're unsure how we got those, try testing some numbers to make sure it makes sense to you. If you try something like 5, you'll find that the square root is going to be a positive number, which is what we need, and 5 is greater than the square root of 2. If you pick something less than negative root 2, like negative 10, and you square it, you get 100 minus 2, which again is a positive number. And if you test anything in between, you'll find that whatever is underneath the square root ends up being negative. So we don't want anything between negative square root of 2 and 2. So let's move on to the next one, h of g of x. So again, our inside function is e to the x, and e to the x has the domain of all numbers. Our new function, our composite function, is the square root of e to the x minus 2. So again, we have this square root conundrum where we need that whatever is underneath the square root is going to need to be positive. In order for something to be positive, it has to be greater than or equal to 0. So we need to set e to the x minus 2 to be greater than or equal to 0. The result of that is that we need e to the x to be greater than or equal to 2. As long as it's bigger than 2, then the result under the square root will be positive. But we want to be able to define this in terms of x. So algebraically, we can use natural logs on both sides to bring the x down. If you take the natural log of e to the x, the natural log and e are reciprocal functions, and we get that x has to be greater than or equal to the natural log of 2. Because when we take the natural log on the left, we also have to take the natural log on the right. So our domain here is more restricted on the new function, and therefore that will become the domain of the composite function. We need x to be greater than or equal to the natural log of 2. Our final function, h of x, is a little more tricky. So here, the inside function is h of x, which is the square root of x minus 2. In this case, we need x to be greater than or equal to 2. If x is greater than or equal to 2, then what's under the square root will be positive and we'll be okay. The new function, our composite function, is the square root of x minus 2, all minus 2. So that means that we need the square root of x minus 2 to be greater than or equal to 2. So the term on the left has to be bigger than the term on the right when we're subtracting in order to keep it positive. So again, we'd like to write this in terms of x. So we're going to square both sides. That will hold the inequality. So we get x minus 2 is greater than or equal to 4. So when you square a square root, the square root goes away. And when you square 2, you get 4. Solving for x gives me that x has to be greater than or equal to 6 because I added the 2 from the left over to the right. So I look at my two different domains to figure out which one is more restrictive. X greater than 6 is more restrictive than x greater than 2 because there's less numbers from 6 to infinity than from 2 to infinity. So since that's more restrictive, the domain of this composite function is that x has to be greater than or equal to 6. If you'd like to convince yourself, try plugging in 6, 7, 8, make sure it's all positive, and then try something like 5 and see what happens if you run into any trouble. That should be enough to convince you that this is the right domain. Example 8. Because the square roots are so tricky, let's try another one to make sure we got the algebra down. So consider f of x equals the square root of x minus 2 and g of x equals the square root of x squared minus 1. We want to find the domain of the composite function f of g of x. So we start with g of x. We write down what g of x is. G of x is the square root of x squared minus 1. The domain of this function, again, needs for whatever is underneath the square root to be positive. So we have x squared minus 1 has to be greater than or equal to 0, which means that x squared has to be greater than or equal to 1. So again, if we consider the cases on each side, the root of x squared is 1 and negative 1. So that tells me that the domain is that x has to be bigger than or equal to 1, or x could be less than or equal to negative 1. Again, if you're not sure, try plugging in a couple of numbers, and this should convince you. So that's the domain of the inside function. Step 2, we have to figure out what our composite function looks like. F of g of x means that we're plugging in g of x into our f function. So therefore, whenever we have an x in our f function, we're going to substitute in our g function. So we have the square root of x squared minus 1, all minus 2. So again, whatever's underneath the square root has to be greater than or equal to 0. So we have the square root of x squared minus 1 minus 2 has to be greater than or equal to 0, which means that the square root of x squared minus 1 has to be greater than or equal to 2. So again, to get rid of the square root, we can square both sides. So here we have x squared minus 1 is greater than or equal to 4. On the left-hand side, when you square a square root, that goes away. And on the right-hand side, 2 squared is going to give you 4. Again, I can square both sides because I'm dealing strictly with positive quantities. This doesn't work the same way with negative numbers. So here, I'm going to add 1 over to the other side, and I get x squared is greater than or equal to 5. So now that I have that, again, I have to consider the cases for x based on the square root. If x squared has to be greater than or equal to 5, then x needs to be greater than or equal to the square root of 5, or x has to be less than or equal to negative square roots of 5. So again, we're thinking about a number line and thinking about what's more restrictive. So the more restrictive domain is going to be that x is greater than or equal to the square root of 5, or x is less than or equal to negative square roots of 5. Now, when I talk about the number line, sometimes it's a good idea to graph it out on a number line if you're not sure where things fall on the number line. So for example, if I take my original domain, that says that x has to be less than negative 1 or greater than 1. Now, if I were to add on my root 5 and negative root 5, the square root of 5 is approximately 2.2. So that means that somewhere over here is the square root of 5, and somewhere over here is negative square root of 5. So now, if I'm saying I can only include numbers there, that's more restrictive because it's not even including this. So our final answer here is that for the composite function, our domain should be x is greater than or equal to square root of 5, or x is less than or equal to negative square roots of 5. When composition fails. So as you can imagine, when we're considering domains of composite functions and composite functions in general, not every two functions can be composed. And we can look at an example here where we can see where it would fail and why. So consider that f of x equals negative x squared and g of x equals the natural log of x. If we try to compose g of f of x, what's going to happen here is we're going to be plugging negative x squared into the natural log of x. So here, we'd end up with something that looked like this. Now, if your intuition is telling you that something is wrong, then you have a good intuition, because the natural log is not defined for 0 or negative numbers, and every single result we can get from x is going to be something negative. So there's no possible scenario where we could plug something in where we would get anything out. And if there's no values that we can get as outputs, then the composition has failed. However, we could compose f of g of x, because if we went in that direction, we would be plugging g into f, and then we would have negative natural log of x all squared. Here, the domain is going to be that x is greater than 0, but there are outputs that come from this function, and therefore it exists. So the composition g of f of x will not work because there are no possible outputs. However, f of g of x will. It's rare that a composition fails, but it does happen. Consider now decomposition of functions. We spent a lot of time talking about how we can take two functions and use them to compose a third function. Sometimes, however, we start with a composite function and we want to consider what could the original functions have been. Most times that we do this, there are many ways to decompose the function. However, we're looking for ones that feel obvious, and again, there's more than one right answer. So for number 9, let's try to decompose each of the following functions. We start with e to the 2x minus 3. Again, there's many ways to do this, but what I'm seeing is that if we let f of x be e to the x and g of x equal 2x minus 3, then f of g of x will give me e to the 2x minus 3. So I have found two functions that I can compose together to get the function given. So I've successfully decomposed it. Number 2, I have the square root of the natural log of x plus x. Here, if I let f of x equal the square root of x and g of x equal the natural log of x plus x, then f of g of x will give me the square root of the natural log of x plus x. So again, I've found a way to successfully decompose this. It doesn't matter if I had picked f of x to be the square root of x or g of x to be the square root of x, as long as my final composition is placed in the right order. And again, there's more than one way that I could have done this. Let's try two more. So for number 3, I'm going to do something a little wild. I'm going to say f of x equals x to the 5th. G of x equals sine of x. And h of x equals x cubed minus 4. Now here, I've picked 3 different functions to compose. I could certainly find a decomposition using only 2 functions, but here, there are 3 different functions to me, and so I pulled them all out. So f of g of h of x means I'm plugging h into g, and then that whole thing into f. And so that will give me sine of x cubed minus 4 all to the 5th. So again, that's one way that I can decompose this. And again, many functions have multiple ways that you can successfully decompose them. Finally, number 4, if I let f of x equal 4x and g of x equals x to the 4th, then f of g of x will be 4x to the 4th. So that's one way. And just to give you an idea of a second way, because I know I keep saying there's multiple ways, consider now that f of x is going to equal x squared and g of x is going to equal 2x squared. Then f of g of x will equal 2x squared squared, which equals 4x to the 4th. So again, there's no one right way to decompose it, but it's a good idea to start trying these because we're going to come back to this in chapter 3 and look at what we can do with composition of functions. And being able to decompose a function will be a very valuable skill.